Good afternoon, everyone. What we're going to discuss today is Chapter 14, Censored Response Models. So if you could follow along, preferably by looking at the PowerPoint deck, um, we'll be able to handle that. That would be the PowerPoint deck for Chapter 14. As we discussed last time, we dealt with the issue of qualitative choice models where the dependent variable takes on a discrete nature, choices, if you will. Now we're going to consider censored response models, also in the class of limited dependent variable models. And the third class of limited dependent variable models, although we're not going to discuss them because of time constraints, would be integer valued models, that is, models that corresponds to uh, integers or counts. For example, the number of trips you might make to the grocery store, to your favorite restaurant, or perhaps a national park. But today we're going to be discussing censored response models where the dependent variables are discontinuous. And as you can see on slide 3, the two classes of censored response models are Tobit models, pioneered by James Tobit in 1958, and the Heckman sample selection procedure pioneered by James Heckman, the noted labor economist from the University of Chicago in the 1970s. Here are pictures on slide 4 of James Tobin and James Heckman. Uh, Now, censored response models are discontinuous in nature, but they often are subject to some thresholds or constraints, and we see these quite often in economic problems such as price support levels. In other words, prices cannot fall below a certain level. For example, loan rates in agriculture. Those would be lower limits, or the lower limit for consumer purchases, of course, would be 0, but there could also be positive values. That's probably the most common situation for a lower limit. But we can also have upper limits dealing with, let's say, acreage restrictions or import quotas, particularly in international trade. So what would happen if one were to ignore the discontinuity in the dependent variable and just go ahead and apply OLS? Certainly, OLS can be used. The downside of OLS is that it produces biased and inconsistent estimators. So we need procedures to better handle the censored response models to allow us to estimate consistent estimates of the explanatory variables in our model. And there's been a fair amount of work in demand analysis, particularly geared to the zero expenditure problem. And to illustrate that, there's a number of works that have been listed on slide 6, plus you'll get an opportunity to deal with censored response models in the bottled water example in problem set 4, number 3, both the use of the Tobit procedure and the Heckman sample selection procedure. The other thing about censored response models, similar to qualitative choice models, is the calculation of correct marginal effects. Remember the three basic outputs that we like to generate from any econometric analysis. What are the statistically important factors affecting the dependent variable? What are the correct marginal effects? That is, if should you realize a unit change in an explanatory variable or a percentage change in an explanatory variable, what would be the corresponding change or percentage change in the dependent variable? The uh, marginal effects analysis are certainly not straightforward with censored response models, and owing to a decomposition of a couple of economists named McDonald and Moffat, we get the correct marginal effects for the Tobit model, and the correct marginal effects for the Heckman procedure was developed by Saha, Capps, and Byrne. Yes, I was part of that team in 1997 that produced the correct marginal effects, and we will talk about that when we get to the Heckman sample selection procedure. If you'll note on slide 8, there's a representation of the Tobit model, either with 0 as the lower limit, another lower bound that we might call alpha I, some sort of price support level, and also an upper bound. We can deal with that as well. And in rarer cases, perhaps we would run into a situation where there would exist both ceilings and floors, particularly on wage rates. But what we're actually going to be discussing here and what problem set 4 deals with is the more popular case of the discontinuity in the dependent variable corresponding to a lower limit of 0. Slide 10 and slide 11 are very important slides because with the use of the Tobit model, we would be in a position to not only estimate the parameters, make predictions, but also get marginal effects. And you'll see equations 1 through 6 expressed on slide 10, and on slide 11, a delineation of what the various arguments are. So in the case of the lower limit of 0, we would specify our model as we always have. And in fact, several of you are doing research problems where you run into this situation. For example, we have a group that's dealing with household purchases of plant-based milk. Some households don't purchase plant-based milk at all. Others record a positive expenditure. The situation there is, well, how do we use the Tobit model? Well, the first thing is you would specify your model just as you've always done. So X on slide 10 would correspond to the set of explanatory variables: household size, household income, price, a vector of socio-demographic variables. And you'll also see on slide 10, importantly, what we might be able to generate as a result of the Tobit specification. Before getting into details, realize with the Tobit model, 2 types of effects or predictions are going to emerge. The first is a prediction unconditionally of what the dependent variable would be. And in our plant-based dairy milk example, the prediction of the amount purchased by anyone. And that would correspond to equation 2 on slide 10. And we also get a conditional prediction, that is, if we assume that a purchase is going to be made or was made, what would our prediction be there? If you'll note, neither equation 2 nor equation 3 is going to be equal to the product of the estimated coefficient beta times x. That's why OLS is inappropriate. And you'll see in equations 2 and 3 the variable z. Now let's describe what z is. We looked at z in the case of qualitative choice models. And in the case of qualitative choice models, z was that linear combination of the estimated coefficients beta with each of the explanatory variables. Don't forget to include the intercept as well. But in the case of the Tobit model, we're not assuming a standard normal distribution. We're assuming a normal distribution with mean 0 and variance sigma squared. So we're going to have to normalize that index by dividing by z. So what will happen when you estimate the Tobit model, and we'll discuss the estimation procedure momentarily, one will get estimates of the coefficients associated with the explanatory variables, but importantly, we will also get an estimate of sigma, which has to be positive. So once we have z, that normalized index, we can then proceed to get the standard normal density function and the cumulative standard normal density function. And the cumulative standard normal distribution function has to be between 0 and 1. So if we go back and take a look at equations 2 and 3, the unconditional prediction or expectation of the dependent variable is the product of x beta times capital F of z, which can be interpreted as the probability of being above the lower limit. But we're also going to have to add to that the product of sigma times little f of z, the probability density function of the standard normal distribution. If you look at equation 3, which is the conditional expectation, we see that's equal to x beta, the linear combination of the estimated coefficients times the explanatory variables, plus another term here, which is sigma times the ratio of little f of z to capital F of z. Now that ratio is very important, and in fact it has a technical name. It's called an inverse Mills ratio. So once beta is estimated, sigma is estimated, we get z. Once we get z for each observation in our sample, according to our model specification, we get the unconditional expectation equation 2, but we also get the conditional expectation. And since the conditional expectation assumes that purchases were made, that is, you're not at the lower limit of 0, the expected value of y, equation 2, must be less than the expected value of y star or asterisk. Equations 4 and 5 deal with marginal effects. And as was the case with Logan and Tobit models, the estimated coefficients, the betas, associated with the explanatory variables are not the marginal effects. To get the unconditional marginal effect, equation 4, we have to multiply the estimated coefficient times little f of z. And remember, or capital F of z, the cumulative distribution function. But since that has to be between 0 and 1, the actual marginal effect is going to be less than the estimated coefficient. In equation 5, which deals with conditional marginal effects, you get a rather complex equation here where you take the estimated coefficient and multiply it by 1 minus z times little f of z divided by capital F of z minus little f of z squared divided by capital F of z squared. And while it's not delineated, keep in mind that the ratio of little f of z to capital F of z is called the inverse Mills ratio. And finally, in equation 6, we can actually see how the probability of being above the lower limit of 0 is affected with unit changes in x. And that expression is given by little f of z times beta over sigma, something very similar to what we calculated in the case of Logan and Tobit models. These expressions actually come from a paper as delineated on slide 11 from the work of McDonald and Moffat in an article in the Review of Economics and Statistics in 1980. On slide 12, we actually see how to estimate the Tobit model. And to make a long story short, we're going to formulate a likelihood function, assuming normality, as Tobin did. And by the way, Tobin, similar to Heckman, each won a Nobel Prize because of this work. And McFadden, when we were discussing his work with Logan and Tobit models, he also won a Nobel Prize. So dealing with these type of models are very important in empirical economics. The likelihood function, as exhibited in slide 12, is arranged in two pieces. The first piece, corresponding arbitrarily to the first n1 observations, say, is actually a representation of the probability of being at the lower limit of 0. The second piece represents the density function when the dependent variable is not 0. And that occurs for observations n1 minus n1 plus 1 minus, or n minus n1 altogether. So by arranging these, we formulate the log likelihood function, and then based on algorithms, you get two situations here: estimated coefficients of beta and sigma. The estimated coefficients of beta allow us to determine which explanatory variables are affecting the dependent variable, and we also get that parameter estimate of sigma. So to illustrate, on slide 13, we have 20 observations. 14 of them, if you'll note, deal with a dependent variable where the lower limit is 0, and 6 of them are above that. We're hypothesizing that x1 and x2 may have an effect on y, and we have our data in that situation. Now, depending on the package that you have, you need to specify your model and also specify the fact that you have a lower limit or an upper limit and what the lower or upper limit would be. So on slide 14 in SAS, for example, where you see the comment asterisk Tobit analysis, if you were a SAS user, you would use procQlim to handle this problem. Below the procQlim specification, you'd have a model statement similar to what we've seen all semester, the dependent variable being y, and the two explanatory variables being x1 and x2. And then we have another statement, native only to SAS, I suppose, where one has to specify what the endogenous variable is, and in this case it's y, with the tilde and the word censored, and in parentheses LB, lower bound, equaling 0. And importantly, with the output statement, at least with SAS, one is able to retrieve the conditional expectation, the unconditional expectation, and some marginal effects. And we'll talk more about that in a problem. Now, to help us here, I've written in the next two slides, slides 15 and 16, the statements that you would need to capture all of the information on slides 10 and 11 that were originated by McDonald and Moffat. So if you'll see the expression z, you would get the linear combination of the estimated coefficients times the explanatory variables. That's the expression x beta underscore y. But remember, we have to normalize z through the estimate of the sigma parameter. And in this case, even though we haven't shown you the estimates yet, the sigma parameter turns out to be 11.718546. So before you do this slide and all the calculations that ensues, one has to estimate the model first. Now, if you're a SAS user, SAS does not provide Z directly. SAS also doesn't provide capital F of Z, which I've written as cap FZ, but we can get that through a command called prob norm. Little f of z is the standard normal density function, and little f of z, its expression is given as e to the negative z squared divided by 2 divided by 2.5066272. That 2.5066272 is actually the square root of 2 pi. Now to get the expression for the unconditional prediction or expected value, which we're calling expected underscore y, we see that expression. We also get the expression here for the conditional expected value, and SAS actually captures both of these. And the expression for the conditional expected value is given on the slide 16. We also then provide slides to determine, similar to that McDonald and Moffat decomposition, the unconditional marginal effects as well as the conditional marginal effects. So the numbers in blue are actually parameter estimates. The 11.718546 is actually the estimate of sigma. 15.151408 is the parameter estimate of x1, and negative 6.313204 is the parameter estimate of x2. All of the expressions here mimic the McDonald and Moffat decomposition, and in problem set 4, question 3, you get to do this same type of calculation for bottled water. Now, how do we then go about using these parameter estimates? Well, on slide 18, if we were to ignore the discontinuity of the dependent variable, one could apply OLS. You'll see the R squared there, 0.2443, the adjusted R squared 0.1554. And you see the parameter estimates for the intercept, x1 and x2. And as it's written there, the parameter estimate for x1 is 3.8871. Its p-value is 0.0360, so x1 turns out to be a driver of the dependent variable. The parameter estimate for x2, negative 1.93564, but its p-value is 0.4598, and one would conclude that x2 is not a driver. Now, but the problem with the use of OLS is that they produce biased and inconsistent estimates. So we're going to use the QLIM procedure here, or if you're a Stata user, a maximum likelihood routine, or an eViews user, a maximum likelihood routine, the same thing with R, to actually derive the parameter estimates for x1, x2, and now sigma, and that's exhibited on slide 20. And as we referred to before, sigma is 11.718546. Sigma 2, x2, the parameter estimate, negative 6.313204, not statistically significant. And the parameter estimate for x1, 15.151408. As you can see, the parameter estimates here with the Tobit model are quite different than the parameter estimates from OLS on slide 19. Now, we do have a maximum likelihood routine. The optimization method as given on slide 20 is the Newton-Raphson technique. And interestingly enough, if one had competing model specifications with the same dependent variable, QLIM also provides the AIC and SIC criteria. Now, what I've described on slide 21, I've obtained the marginal effects, the unconditional marginal effects, the unconditional expected value or prediction, and the conditional expected value or prediction for each of the 20 observations. Some of these are given by SAS, some of them are not, and depending on the package, you may or may not get these, but we have the expressions such that with the parameter estimates of beta and sigma, we can get z, we can then get little f of z, capital F of z, we can derive all of this information. And note that these marginal effects and predicted values vary from one observation to the next. And here on slide 22, you get the corresponding values of z, cap f of z, little f of z, and the same thing is true on slide 23. And again, you'll get an opportunity to do these calculations with that sample problem involving bottled water, except instead of having 20 observations, you're going to be dealing with 7,195 observations. Now we can summarize all of these marginal effects by using the mean or a median, that is averaging these, and all of that information is given on slide 25. Alternatively, we could calculate the index z at the sample means of the data, and then get a representation of little f of z, capital F of z at the sample means. So instead of having to do this for each observation, we would do one computation at the sample means. Now the final point to be made here is, what about a goodness of fit associated with this Tobit model? Well, what we can do is obtain the unconditional expected value of the dependent variable, which we're referring to here as expected underscore y, and take the correlation of that variable with the actual y value, which has 14 zeros and 6 non-zero values. Turns out in this case, the correlation of the two variables is 0.43281, but if we were to square that correlation, we would get an r squared. Many analysts, when they use the Tobit procedures, fail to provide an r squared because perhaps the package they're using won't produce that. But in any case, no matter what package, using this procedure of obtaining the correlation of the dependent variable with the expected unconditional expectation, one should be able to derive an r squared. And it's very similar to the r squared that we got with OLS. So what is the weakness of the Tobit model? Well, before we get to the weakness model, let's talk about the strengths. The strength is you get to focus on unconditional and conditional behavior, the marginal effects of unconditional and conditional behavior, and you're able to understand how the probability of being above the lower limit, 0 in this case, changes with changes in the explanatory variables. The basic weakness of the Tobit model is that it assumes the decision to purchase or consume is the same as the decision about how much to consume. And as been pointed out by Haynes, Gilkey, and Popkin on slide 27, ignoring the two-step nature of the decision process when it comes to consumption decisions, they argue may hamper understanding of the true behavioral patterns, lead to erroneous conclusions, and generate incorrect policy recommendations. That's the principal weakness with the Tobit model. And in the past, before advances in software, the number of 0 observations, if that number was rather sizable, often the maximum likelihood procedure for the Tobit analysis broke down. But with the advances that we've made, this is not typically going to be a problem, no matter how many percentages of zeros we actually have. So that concludes the Tobit model. Now let's take a look at the Heckman sample selection procedure to round out our discussion on censored response models. Using an approach that's different, the temptation for any analyst is to take the lower limit values, 0 in our case, 0 in your problem set dealing with bottled water, and just omit them. We actually did that when we were dealing with the discussion of heteroscedasticity in an earlier problem set 2. The argument, though, is that's not a viable thing to do, or to ignore the zeros altogether, just go ahead and estimate them, and as we've seen, that would lead to biased and inconsistent estimates. So if one is tempted to throw away the zeros, Heckman argues, and he had 2 separate papers in 1976 and 1979, the idea is that if one were to do that, there is a possibility of sample selection bias associated with your model. Heckman then found that to avoid the sample selection bias issue, one could throw away the zeros and then use the non-zero observations. But if we're going to do that, we have to append a particular variable to our model specification. And that variable corresponds to the inverse of Mills ratio. In fact, the expression on slide 28 looks much like the McDonald and Moffett equation 3, so we're only focusing on conditional um, expectations or conditional purchases with the Heckman sample selection procedure. The question is, where do we get the inverse Mills ratio? And as it turns out, the Heckman procedure, operates in two stages. In the first stage, one of which you're intimately familiar by now, is to use a Tobit analysis, using all of the observations. The dependent variable is 0 or 1, and we had a whole lecture on that, and we also do that on problem set 4, question number 2 with bottled water. Now, well, the reason we use Tobit analysis instead of logit analysis is due to the assumption of normality that Heckman uses. So once we do the Tobit analysis, and we can get all of the information that we had before, but now the important feature here in the first stage of the Heckman procedure is to get an estimate of the inverse Mills ratio, or IMR, as I describe it on slide 29. So second stage, get IMR, add it as an additional explanatory variable. Don't use the zeros, just the non-zero observations in the second stage, and employ either OLS or GLS, because, as Heckman points out, there is the possibility of potential heteroscedasticity with the Heckman procedure. So you'll see the details of this laid out on slide 30 as to how we get the inverse Mills ratio, from the use of the Tobit model. And on slide 31, we see, the model specification there with an appended coefficient alpha times the inverse Mills ratio. Now, the reason that's important, if alpha turns out to be statistically different from 0, that means there would have been sample selection bias if you've thrown away the zeros. However, if alpha was not statistically different from 0, one would have been very lucky to throw away the zeros and not have bias or a sample selection bias in the sample. But in many cases, alpha usually turns out to be statistically significant evidence of the sample selection bias. Now, slide 32 is also a complicated slide in the sense that, as I said earlier, Heckman pointed out that with his procedure, there's prospect for potential heteroscedasticity. So how do we get rid of that? Well, if you'll remember the lecture on heteroscedasticity, we would use weighted least squares, or I referred to it here also as generalized least squares, but weighted least squares. And the weight, you see, is given in the middle of slide 32 as 1 divided by the square root of 1 plus delta hat times sh hat lambda hat minus lambda hat squared. So what are each of these values? Let's start with s sub h hat. S sub h hat is nothing more than the variable z that we would get from the Tobit model, the linear combination of the explanatory variables w here times their estimated coefficients gamma hat. Lambda hat is the inverse Mills ratio that was previously described. And what is delta? Delta is obtained by estimating the squared residuals after the application of OLS, something that we typically would do in dealing with heteroscedasticity. But the right-hand side variable then turns out to be s sub h lambda h minus lambda squared. If delta turns out to be not different from 0, as we describe on slide 33, well, then OLS is the correct estimation procedure. But if delta is significantly different from 0, the appropriate procedure to circumvent the potential heteroscedasticity problem is the expression that was given on slide 32 in the middle of the page. The only fly in the ointment here is that because the weight involves the square root, it's necessary for that expression to be positive, and we can't always guarantee that. So even if potential heteroscedasticity is evident because delta is significantly different from zero, we may not be able to produce the weight for all observations. Now, one other thing about marginal effects here with respect to the Heckman procedure, and this is the contribution that I made 23 years ago with the work of my colleague Atanu Saha, who was on the Texas A&M faculty at the time, and my graduate student Patrick J. Byrne. And if you'll note on slide 34, the marginal effect is really decomposed into two pieces. The beta sub j is actually the estimated coefficient that we would get with each explanatory variable in the application of the second stage of the Heckman procedure. But we also need to deal with the change in the inverse Mills ratio due to a change in an explanatory variable as well, and that's multiplied by the coefficient alpha. Why is that? Because the IMR is the ratio of the probability density function divided by the cumulative distribution function. Each of those involve a linear combination of the x's and the estimated coefficients. So in order to capture the appropriate marginal effects, we need to use this expression to calculate appropriately the correct marginal effects with the use of the Heckman procedure. Now, if it turns out that alpha is not statistically different from zero, that is, no sample selection bias, the calculation of the marginal effects for the Heckman procedure is simple. It's just beta j for the jth explanatory variable. But if alpha is significantly different from zero, then the marginal effects are not equal to that estimated coefficient. And on slide 35, after much algebraic steps and after much simplification, I give a representation for what the correct marginal effects should be. Now, to go to our example here, one that you're going to be dealing with the purchase of bottled water, and you'll get a chance to deal with the Heckman procedure on problem set 4, question number 3 as well. So in the first step of the Heckman procedure, we would simply use the Tobit model that we talked about before. And basically, even though we can get a lot of information from the use of the Tobit model as we described in the lecture on qualitative choice models, what's important in the Heckman sample selection procedure is the retrieval of the inverse Mills ratio. And once we have that, then in the second step, we can delete all observations wherein the dependent variable happens to be zero. So you'll see an expression here on slide 38 where the dependent variable is the natural log of BW gallons equaling our explanatory variables being the natural log of price, the natural log of income, region, with West being the base category, black and white with the base category being any other race. And now what is highlighted in that red box is the inverse Mills ratio. Most packages allow you to retrieve that variable, but if not, one can create that as well. And then at the top part of slide 39 is a demonstration to determine whether or not we need to correct for heteroscedasticity. And if that estimated coefficient delta, as we described on earlier slides, is not statistically different from zero, then we can use OLS and not have to worry about weighted least squares. So in the case of your homework problem, here's a representation of descriptive statistics and the mean with 7,195 observations. As we've seen earlier, 2/3 roughly of the sample purchased bottled water. and that's the mean of 0.68075505. We see the mean gallons purchased, the mean expenditure. I didn't represent a mean price because I didn't impute the price in this particular example, but in your homework, you need to impute the price for missing price observations, the situation wherein BW gallons and BW EXP are equal to 0. So now what we do is, in the first step, use the Tobit model. And you'll see a goodness of fit here for the Tobit model. You're asked to do that anyway on problem set 4, question 2. But again, the principal thing to get out of this is the inverse Mills ratio. But let's suppose we didn't do that. We just use all of the observations in our sample, all the non-zero observations in our sample and applied OLS. You'll get those results exhibited on page 44. And what's highlighted with the parameter estimates, these in fact turn out to be the marginal effects, but there's no adjustment for sample selection bias. You also see highlighted in the last column the boxes where the p-values are less than 0.05, indicative of statistical significance. Now, what happens when we make the adjustment for sample selection bias? Well, we add or append to our specification this variable Mills underscore drink BW, and you see that estimated coefficient on slide 46 being 118.3052. But notice its p-value is 0.0409, meaning we do have sample selection bias. By the way, this coefficient that's highlighted 118, that's what we've been calling alpha. Alpha could be positive or negative. The question is that coefficient statistically different from 0? And in dealing with heteroscedasticity, we see that in running that auxiliary regression, there's no evidence of heteroscedasticity, so we're fortunate and only have to worry about the use of OLS. And on slide 48 here, we're almost finished, we have a summary of what's going on with this bottled water example. Now, the explanatory variables in my analysis are a little different than those that are going to be evident in your homework, but it'll be very similar. We have a column here called the Tobit coefficient, and we see all the coefficients there in column 2 for income, East, Midwest, South, Black, White, Price, etc. And these represent the estimated coefficients that one would get through the use of the Tobit model. And if you'll look on the row labeled X beta, that at the sample means, what I've calculated here, that is the sample means of the explanatory variables here, we're able to get the value of Z from the Tobit model, or we could just call it X beta. We also get the IMR of 0.5252, that is little f of Z divided by capital F of Z. The third column, the second stage coefficient, is just a representation of what we get with OLS when we append the inverse Mills ratio. And the next column would be what would happen if we just use OLS, using only the non-zero observations, but not making any adjustment for sample selection bias, that is the last column. But the next to the last column, you see the appropriate marginal effect with the adjustment for sample selection bias. The expression is given at the bottom of the page. And if you'll note here, the appropriate marginal effects are quite different than if you didn't get an adjustment, or if you made no adjustment for sample selection bias. The only exception to that rule is for price, and the reason is price was not involved in the Tobit estimation, but in your homework, price will be involved in the homework. So you're not going to get the same marginal effect with or without the adjustment for sample selection bias. So to conclude this lecture, we got two choices, popular choices for dealing with situations, typically cross-sectional data, wherein the dependent variable is censored or discontinuous. One could use the Tobit analysis or Heckman sample selection procedure. Heavy emphasis of conditional behavior on sample selection procedure. But if you wanted unconditional behavior, Tobit analysis would be the way to go as well. And in all cases, whether it's qualitative choice or censored response, careful consideration should be given to the calculation of the appropriate marginal effects. So my friends, stay well, stay safe, and we'll have the next lecture dealing with panel data coming up. Thank you so much. Bye-bye.